Okay, so I'm going to do this to help you guys out a little bit. I know in the earlier classes I got through some of this, the later classes I didn't. These are the equations you're going to be given, and you're always going to get them. You're probably not going to need them after you do it for a little bit, but those are the two equations. This one over here is going to be for like the individuals, if they give you like a number of rabbits or squirrels or something, and over here for the alleles, which are a little less likely, but sometimes. So what is the Hardy-Weinberg symbol for the frequency of the dominant allele? That's going to be P. Frequency of the recessive allele is Q. Remember, those are the alleles. What's the symbol for the frequency of the homozygous dominant genotype? So like big A, we're going to use P squared. Heterozygous A little a is going to be 2PQ. And homozygous recessive little a would be our Q squared. Remember, this is the frequency, so they're percentages. If the allele frequency of R, like a lowercase r, is 0.75, what's the frequency of the capital? Well, if 75%, there's only 25% left. Big R was the frequency of little r, 0.85. Okay, these have to equal 1. This is basically P, this is Q. In this case, this is Q, that's P. Easy, let's keep going. Switch it up, black to red. In a population, the homozygous dominant, big A, or our P squared, makes up 81%. Let's change that to 0.81. Heterozygous, which is big A, little a, is our 2PQ, and that's going to make up 18%. We'll change that to 0.18. What's the frequency of the P allele? We can do this in one step, but I want to do everything to kind of double check. I set it up like this. P equals Q equals. We want both of those to add up to 1. Then I have my P squared. I have my Q squared, my 2PQ, and all of those are going to add up to 1. What do I have? Well, my P squared, 0.81. I have my 2PQ as a 0.18. I could easily find my Q squared right now just by simple subtraction, but I think it's actually a little bit easier to find your P first. What's the square root of 0.81? 0.9. 1 minus 0.9 is 0.1. 0.1 squared is 0.01. I add these up, equals 1, I'm all good. Honestly, you could have just taken this and directly gotten your P from it, because that is P squared. Take the square root of it, you get your P. But by doing this, you make sure all your numbers work out. You didn't do anything wrong, everything equals 1 or 100%. Tay-Sachs. Tay-Sachs is actually a deadly disease. Okay, you're not going to live to reproductive age, so that'll come up in a little bit, but it's a recessive allele. So if you have Tay-Sachs, little a, and unfortunately you're not going to live past the age of 5. So the only people around that have this are carriers. Since it's recessive, it doesn't show up in them. The frequency of this allele is 0.1 in a population of 3,600. Okay, it's the frequency of an allele. It's the recessive allele. A equals Q equals 0.1. Okay, Q equals 0.1. P equals 0.9. That equals 1. Q squared equals 0.01. P squared equals 0.81. 2PQ, that's the worst Q ever, equals 0.18. You must be so impressed by my math until you realize it's the same numbers here. Okay, I don't like doing this. I'm sorry that they're both the same, but hey, it's what we got. Okay, whole bunch of questions here. What is the frequency of the dominant allele? Well, that's P. My P equals 0.9. Easy. Let's keep going. How many people will have Tay-Sachs? Okay, well, that would be my Q squared. Those are my people. So that's Q squared equals 0.01. That's 1% of 3,600. So you multiply that by 3,600. We get 36 as our answer. 36 individuals will have Tay-Sachs in this population. How many people don't have? Well, that's technically P squared plus 2PQ, but why do all that math? just take your 3,600 and subtract your 36 from it. And you're going to get 3,564. And how many are carriers? Okay, so that's our 18% times our 3,600. And that's going to give us our 648. Now, a little bit of a caveat here. This is never going to be in Hardy-Weinberg equilibrium. It's impossible for this to occur. The reason why is this lethal recessive phenotype. That means that these 36 individuals are not going to survive to reproductive age. They're not going to put their genes back in the gene pool. That's going to change our frequencies. Everything's going to get messed up. So if you were to come back to this population, the frequency of the allele would continuously be going down because there's no way natural selection is not occurring. No, there isn't a predator, there isn't an outside force. They're just straight up dying before reproductive age. So we're not going to be able to maintain these allele frequencies. So this one will never stay in Hardy-Weinberg equilibrium. These are like the predicted numbers. These are the things that like we should see, but in a real population, you would never see it. Last one is by far the most challenging. Okay, this is what you'd end up with a quiz, test, AP exam. Okay, everything we do up to this point is like teaching us. This one is pure application. Scientist, researcher goes out into the field and actually observes phenotypes, sees these birds and their phenotypes. So take a second, pause the video, work it out. First thing I'm going to guess is you assumed that round beak was dominant and pointed beak was recessive. Now, why? Because there's more round beak and less pointed beak. But if you paid close attention, it actually says round beak heterozygous. It tells you there the heterozygotes are round. That means that this is the dominant trait. First step is you have to find your total population. Let's add them up. 10,084. Honestly, don't ever use the dominant because that is going to be P plus 2PQ. You have two variables in there. That's way too hard. Forget about it. I'm not going into advanced freaking algebra, calculus, whatever it is to figure out two variables at once. Let's do this. 1,128 divided by 10,084. That's going to give us our frequency of recessive individuals. How often do you see a pointed beak? We come out to about 0.11. That's rounded. That's going to be little a. That's Q squared. Where do we go from here? Well, Q squared alone didn't give us anything except for Q. What's the square root of 0.11? Well, our Q is going to be 0.33. Now we could find our P, 0.67. Now we work back. We have our P squared. So 0.67 times 0.67 is 0.45. And our 2PQ is going to be 0.44. We add those up, we equal 1. We add those up, we equal 1. Yep, everything's good. What the heck's the question? What proportion of future populations expected to be round beak heterozygous? That's our 2PQ. That's this number right here. 0.44 is the answer. If we wanted to guess what part of the population is that, we would just multiply this by our total population. Then we get the number of heterozygotes. Okay, hope that helped and you can move forward and try some other ones.